Okay, so the problem wants us to find the horizontal reaction force that is acting upon the obstruction. What it gives us is a 70 centimeter height at the left, a 10 centimeter height at the right, a 50 centimeter height of the obstruction, and a 150 centimeter width. So we can assume it's a rectangular channel with a constant width of 150 centimeters. We can also neglect viscous effects. We can assume uniform velocity profiles, and we can do our business. We'll start off with identifying the unknowns. We have the velocity at the left side, the velocity at the right side, and the big kahuna, the reaction force of the obstruction. So since we have three unknowns, we need three equations. Off the top of my head, I thought of the conservation of mass, Bernoulli, and momentum equations. Considering the conservation of mass, it seems pretty good because we have a mass flux going in, mass flux coming out. There are no other channels, so we have that continuity. So conservation of mass can be used. Check. Bernoulli equation. All the assumptions for the Bernoulli equation are fulfilled, including the viscous effects being neglected and uniform velocity profiles, so that is good. Check. And the momentum equation, we can certainly use the momentum equation. Check. So first we'll go with the conservation of mass. The general form of it is V1A1 equals V2A2. But since we have a uniform width in the rectangular channel here, we can take away the areas and replace them with the heights of the channels, which are 0.7 meters. Sorry for the typo. And 0.1 meters. And if we solve that equation all through, we get V2 equals 7V1. So keeping that in mind, we have it up in the upper right corner there. We have the Bernoulli equation now, which since we are going to take the Bernoulli equation along a streamline at the top of the flow, we have a gauge pressure of 0. So we have V1 squared over 2G plus H1 is going to be equal to V2 squared over 2G plus H2. We'll sub in a few values here, including the 7V1 for V2. So we square that, it becomes 49V1 squared. And then solving this through gives us V1 equals 0.495 meters per second, and V2 equals 3.466 meters per second. So now since we have two of our unknowns, we can move on to the third equation, which is the momentum equation, which gives us the sum of forces in the x direction is going to be equal to the mass flow in the x direction times the difference between the second velocity and the first velocity in the x direction, so we can just use speeds. First we'll figure out the mass flow. Equation for mass flow is density times the velocity of a particular point times the area of a particular point. So that gives us the flow rate times the density in order to give us a mass flow rate. So subbing some values in, we have 1,000 kilograms per cubic meter times 0.495 meters per second times 0.7 meters times 1.5 meters, all multiplies out to give us 519.75 kilograms per second. So now we can bring that back to the momentum equation, except we still haven't figured out what exactly those forces are. So we're going to have to identify that. To do that, we'll use a control volume. So here we have it. It's not too close to any turbulent activity. We still have uniform velocity at all at the starting and the ending points. So we can use this nice thing, and it has three forces acting on it, three approximate forces. We have F1, which is the resultant force of the pressure on the left side, F2, which is the resultant force of the pressure on the right side, and the reaction force of the obstruction against the fluid. So with that, we can build this sum of the x forces. F1 subtract F2 subtract Rx equals the sum of forces. Now talking about the F1 and the F2, which are the resultant forces of the pressures. What we want to do is use the average pressure of the surface that the pressure is acting on and multiply that by the area. So for F1 we have the average pressure at 1 times the area of 1, right? And substituting some earlier equations we learned, we have the specific weight of water times 1/2 of the height at 1. That's going to give us the average pressure. And then multiply that by the area. So we have H1 times W. And likewise for F2. And we're just going to solve for the difference between F1 and F2 because that's what is reflected in our equation up there. That gives us a value of 3,531.6 newtons. So now substituting the values we just found out back into the momentum equation, we have that number we just solved for, subtract Rx equals 519.75 times V2 subtract V1, which is 3.466 meters per second, subtract 0.495 meters per second. Multiplying all those values through and solving for Rx, we can find out that the reaction force that the obstruction is placing upon the fluid, and therefore by Newton's third law, the horizontal force that the fluid acts upon the obstruction is 1,987 newtons.